All right. So good morning or good afternoon, everyone. It's my pleasure to introduce the speaker of today. So Yanxu Chen is an oceanographer specializing in air-sea coupling processes, mainly induced by ocean mesoscale eddies. She recently completed her postdoc appointment at the Woodsole Oceanographic Institution and has just moved to Dalhousie University in Canada. Her research investigates how ocean mesoscale variability regulates heat momentum and carbon exchange between the ocean and the atmosphere, and she exploits different approaches ranging from satellite data, in situ observations, and modeling data. Today, she will mainly present her work published in JGR Ocean this year, and it deals with stability and air sea fluxes from sail-drawn data. So please, Yanxu, the floor is yours. Thank you.
Yeah, thank you, Agostino. And hi, everyone. Thank you so much for joining. I'm Yanxu, and this is a study I carried out during my postdoc period at the Woodsole Oceanographic Institution. So I've now just moved to Dalhousie University, where I continue to study air-sea interactions, expanding this line of work towards air-sea carbon flux more. So what I will share today is from our recently published paper in JGR Oceans entitled Impacts of Atmospheric Near-Surface Stability on the Arctic Summer Air-Sea Heat Budget. For today's talk, I've shortened the title to Stability Rules the Air-Sea Flux because that's really the story I want to tell. This work was done in collaboration with Dr. Li Sanyu, one of my advisors at Hui, who guided the conceptual framework, and Dr. Chidong Zhang from NOAA PMEL, who helped me better understand the sail-drawn observations and contributed valuable insights for the statistics. Of course, I'd also like to thank the OASIS webinar series organizers, especially Agostino, for the invitation to share this work. In the next few slides, I will show how atmospheric stability controls air-sea heat exchange in the Arctic summer and why this process is central to understanding polar climate feedbacks and potentially future improvements that we can do for the air-sea coupled models. So before going into our results, I'd like to start by talking about why stability matters for air-sea interaction. The atmospheric marine boundary layer, or AMBL, is the layer that directly governs the exchange of momentum, heat, and moisture between the ocean and the atmosphere. On the left, you see three conceptual states: unstable, neutral, and stable. In an unstable atmosphere, for example, when the ocean is much warmer than the air parcels are buoyant and rise easily, so we get strong vertical mixing and large turbulent fluxes. In a stable atmosphere, like when the air is warmer than the ocean, the air parcels are negatively buoyant and sink back down, so turbulence is suppressed and heat fluxes are very weak in this case. And neutral conditions lie in between, shear-driven but not buoyancy-driven, and that's actually where much of the Arctic summer falls. On the right, this is a schematic comparing vertical ocean temperature profiles in the tropics, mid-latitudes, and polar regions. You can see that in mid-latitudes, there is a clear seasonal contrast between summer and winter, especially summer when the vertical gradients are strong and models tuned for those regions perform very well. But in polar regions, and also in the summer, the near-surface air temperature is often very close to the sea surface temperature, meaning the boundary layer is near neutral. And that's where the problem arises. The bulk flux schemes like the core algorithm everyone uses, which are tuned for tropical conditions, often underperform in this near neutral Arctic regime. So the key motivation of this work is, can we better understand and parameterize fluxes under this weak gradient near neutral conditions, which dominate the summer Arctic boundary layer? Now let's connect this to the larger climate context, Arctic amplification. On the left, you see trends in melt onset and freeze up dates from 1979 to 2021. The left panel shows that the Arctic melt season is starting earlier by as much as 20 to 30 days per decade in some regions. And the right panel shows that freeze up is happening later, especially across the Beaufort and Chukchi seas. So overall, the open water season has become much longer. On the right side of the slide is the classic Arctic amplification feedback loop. As sea ice retreats, the ocean surface becomes darker and absorbs more solar radiation, warming the upper ocean. That extra heat delays freeze up, which then exposes even more open water the following months. But there's one big question here that hasn't been fully answered. Does the atmospheric boundary layer actually allows the ocean to vent this heat back to the atmosphere? So in other words, we know the ocean is storing more heat because of longer ice-free periods, but how much of that heat can actually escape depends on the stability of the near surface air. So if the atmosphere is too stable, it acts almost like a lid, trapping heat in the ocean. If it's unstable or near neutral, the ocean can release that heat efficiently, influencing both weather and the regional climate system. So to understand where our work fits, let's look at the history of air-sea flux observations in the Arctic. The first major campaign was Shiba from 1997 to 1998, when the icebreaker was frozen into the pack ice in the Beaufort Sea for a full year. And Shiba provides the first long-term measurements of surface energy fluxes over sea ice. And it really laid the foundation for understanding how the surface exchanges heat and momentum in the Arctic winter. Then, more than 20 years later, the Mosaic expedition took place in 2019 to 2020. So this is another year-long drift experiment, but with a much more advanced observational network. And Mosaic focused primarily on the ice cover regime, capturing the transition from winter to summer and back to freeze up. So, and more recently, from about 2018 to 2022, we started to have Saildrone deployments. They are uncrewed surface vehicles that can measure fluxes over open water and into the marginal ice zone, where ships and buoys can't easily operate. So together, these three efforts, Shiba, Mosaic, and Saildrone, cover almost the full spectrum of Arctic conditions, from frozen ice to melting ice to fully open water. And our study builds on that last frontier, using Saildrone data to explore how atmospheric stability controls air-sea fluxes in the summer Arctic, when the ocean is ice-free, but the air-sea heat flux direction is still undetermined. So next, let me introduce the platform we use, the Saildrone. It's a 7-meter autonomous surface vehicle powered by wind and solar energy. So it can operate for months without human intervention, which is essential in remote Arctic environments. On the left, you can see the sensor configuration. It measures winds at 5 to 10 hertz, air temperature and humidity at 2 meters, barometric pressure and sea surface temperature about 0.5 meter below the surface. That's what we call the BOC SST. These platforms have been operated by several agencies, including, of course, the Saildrone company and NOAA PMEL and NASA. In particular, so the NASA-led Saildrone missions are equipped with infrared radiometers that directly measure the skin temperature. Sorry.
All right.
Okay, I'll continue. Measure the skin temperature for the NASA-led Saildrone missions. And the skin temperature is the temperature of the top few microns of the ocean surface that actually exchanges heat with the atmosphere. The diagram on the right shows why that distinction matters. So the skin temperature, which is the red star, is slightly cooler than the water just below it under most conditions because of the cool skin effect. But during daytime with weak winds, you can easily get a warm layer instead. So by combining bulk SST from our CO drone sensors with skin SST from those NASA mission CO drone sensors, we can better understand how those small near-surface gradients influence air sea temperature differences and ultimately heat flux estimates. Here I'm showing the 5-year CO drone coverage from 2018 to 2022, focusing on the Bering-Chukchi-Beaufort corridor, which is basically the highway connecting the Pacific Ocean into the Arctic Ocean. Now, I know many of you in this group work mainly on tropical or subtropical air interaction, where we always have open water. But in the Arctic, that's not the case. The presence and timing of sea ice really define when and where fluxes, especially the air sea fluxes, can occur. And in panel A, you can see the study region outlined in blue, extending from the Bering Strait up into the Beaufort Sea. The panel C below it shows sea ice concentration as a function of latitude and months. You can see how the open water season expands northward in summer, and each red line marks a CO drone mission from 2018 to 2022. All CO drones are in ice-free environments, as you can see. On the right is a map of major ocean currents. The red arrows indicate warm Pacific water entering through the Bering Strait and flowing northward along Alaska, then feeding into the clockwise Beaufort Gyre circulation. So this warm inflow is the primary oceanic heat source in this region as well, just to give you a background of what we have for the ocean circulation there. And now that we've seen where the data come from, let's talk about the framework we use to interpret the air sea fluxes, the Munin-Obukov similarity theory, or MOST. So MOST basically tells us that turbulence near the surface is governed by two main factors, wind shear and buoyancy, just like the Richardson number, as we know and as we usually use in the ocean. It defines a characteristic length scale, the Munin-Obukov length, L, that represents the height at which the mechanical and buoyant production of turbulence are in balance. So when L is negative, buoyancy is enhancing turbulence. That's unstable conditions, typically when the ocean is warmer than the air. And when L is positive, buoyancy is suppressing turbulence. That's stable conditions, such as when the air is warmer than the ocean. And when L is very large, either positive or negative, the system is close to neutral, meaning turbulence is mostly driven by wind shear. We often use the non-dimensional stability parameter zeta equals Z over L to characterize this balance. This parameter allows us to use what we call flux profile relationships. Those are empirically derived universal functions that link mean gradients to turbulent fluxes. So in practice, MOST provides the theoretical foundation for both direct covariance methods, where fluxes are measured directly, and for bulk parameterizations, such as the core algorithm, which estimate fluxes from mean variables. And what's interesting in the Arctic is that, unlike in the tropics, the atmosphere is often near neutral or weakly stable, meaning that these flux profile relationships, which were tuned for tropical conditions, don't always perform well. And that's one of the key motivations of this study. And since we've introduced the Muni-Obikov framework, let's look at the different ways we actually estimate air sea fluxes, depending on what information we have and what scale we are working at. At the top of the hierarchy, we have eddy covariance, or the EC. This is the most direct and physically exact method. It measures the covariance of vertical wind fluctuations with temperature and humidity fluctuations. That is W prime times T prime or W prime times Q prime, depending on whether you use temperature or humidity. And EC gives us the true turbulence fluxes without assuming anything about the stability functions. But it requires very fast sensors and careful motion corrections, which is challenging over the ocean, especially in the Arctic. Then we have the Bach algorithms like CORE, which are based on Muni-Obikov similarity theory. These schemes use empirical stability functions, the phi, derived from EC data and apply them to mean gradients. For example, the difference between the air and the ocean in temperature, humidity, and wind speed. They are less direct, but much easier to apply across buoys, ships, and sail drones. And the third one, as I summarize here, is the flux gradient or K-profile method. So this is another form of the same concept. It uses a diffusion approximation to express fluxes in terms of mean gradients and an eddy diffusivity kappa. This method is often used in models when vertical profiles are available. And finally, at the largest scale, reanalysis or climate models compute fluxes through parameterizations that are, again, derived from MOST, but these are highly smoothed. They prioritize energy conservation and great scale stability at the cost of small scale variability. So there is a clear hierarchy here. So from direct EC to box schemes to model parameterizations. And what we are trying to do in this study is to test where these Bach relationships break down under Arctic stability conditions. So here is an overview of the sail drone tracks from 2018 to 2022, 5 years, which together form the dataset used in this study. Each panel shows 1 year of operation with the colored lines representing the sail drone trajectories and the background field showing surface pressure in color with arrows indicating wind vectors. At the top of each panel is the wind rows, summarizing the frequency and strength of wind directions for that year. The color shading corresponds to wind speed, from blue for weak winds and yellow for strong winds. What's remarkable here is that across 5 years, the sail drones consistently capture a range of synoptic and surface forcing conditions, from warm southerly winds during Pacific inflow events to cold northerly winds under Arctic high pressure conditions. And now let's look at how the air-sea fluxes evolve through the open water season from June to September, to be specific, across the 5 years of sail drone data. And each panel shows the seasonal or temporal evolution for a given year, with the red line for sensible heat flux, blue for latent heat flux, and orange for the sea air temperature difference, Ts minus Ta. The small wind rows on the left, again, summarizes the dominant wind direction and strength for each year. Across all years, we can see a consistent seasonal pattern. Early in the season, like June to July, the sea and air temperatures are similar and the fluxes remain small. So the conditions are stable or near neutral stability. As the open water area expands and the ocean absorbs more heat, the sea surface warms faster than the atmosphere, leading to positive Ts minus Ta, so sea air temperature difference, and a sharp increase in both sensible and latent heat fluxes. By late August and September, these fluxes often peak, coinciding with stronger winds and warmer ocean surfaces. And now we've looked at how the fluxes evolve from summer to autumn. The next question is what actually drives that variability? Here, I decompose the total turbulent heat flux into three main contributing terms. The total flux in red is basically the sum of all the contributions. The T term in blue represents the product of mean wind speed and variations in temperature. And the W term in yellow represents the wind speed variations and time mean temperature. And the C term in orange is the covariance term, is the real covariance term, where fluctuations in wind and temperature interact. So if we look across years, we can see that the temperature difference term dominance, which is the T term, especially in the year of 2019, accounting for 90% of total variance in the fluxes, as shown by the bar plots on the right. And next, I show 5 representative cases across the 5 Seozhong years to contrast warm and cold air advection. So the panels on the left, the 3 panels in red box show warm to cold air advection transitions from 2018, 2019 and 2020. In these cases, winds shift from southerly to northerly, bringing cold air over a warmer ocean, which increases the sea air temperature difference and leads to strong upward turbulent heat fluxes. On the right, in blue box, are cold to warm advection transitions from the year of 2021 and 2022. Here, the winds switch from northerly to southerly, carrying warm air over colder water, stabilizing the boundary layer and suppressing the upward heat fluxes. So just by reversing the wind direction, we can switch between regimes where the ocean releases heat to the atmosphere and those where the atmosphere caps the exchange. Here, I still focus on 2 contrasting scenarios, which is like the 2 contrasting summers of 2020 and 2022, to see how the type of air advection affects the structure of turbulence. In 2022, we had persistent cold air advection events, cold, dry air flow over warmer ocean surfaces, creating strong instability and continuous turbulent mixing. The power spectra on the top show that both the turbulent heat flux and the temperature difference follow steep slopes around -4, meaning that most of the energy is concentrated at larger, slower scales. This reflects persistent organized convection. And in contrast of the year 2022 was dominated by warm air advection with short episodic bursts of instability. The spectral slopes are much shallower, around -3, showing more high frequency variability. In other words, the system is more intermittent and less organized. So my conclusion is, under cold air advection, we see a steady, large-scale turbulent regime, while under warm air advection, turbulence becomes patchier and dominated by small-scale bursts. And to put my results in context, this figure from Kurtman et al. 2012 shows how the coupling between sea surface temperature and turbulent heat flux depends on spatial scale. In the upper panels, the red shading shows positive SST turbulent heat flux correlations, where fluxes respond to existing SST anomalies. This coupling tends to occur at the mesoscale, for example, along western boundary currents or frontal zones. In contrast, the lower panels show SST tendency and turbulent heat flux correlations, which are strongest and negative at the large scale. That means at at large scale, fluxes drive SST changes. The atmosphere acts as the forcing. So in short, at the mesoscale, SST controls fluxes, and in the large scale, fluxes control the SST. And my Seldon study focuses on such comparison as well. So building on the global framework from Kurtman et al., we can now look at how this coupling behaves in the Arctic Seldon observations. And these plots show the SST turbulent heat flux coupling coefficient for two contrasting years, still the 2020 when the atmosphere was mostly unstable and 2022 when it was stable. In 2020, the correlation is positive, about plus 30 watts per meter square per Kelvin, meaning that the warm SST anomalies drive upward heat fluxes. The ocean forces the atmosphere, consistent with the global mesoscale coupling. And the corresponding spectrum on the right follows a key to -3 slope, again suggesting organized turbulence. And in contrast, in 2022, the correlation flips negative around -45 watts per meter square per Kelvin. Here, the atmosphere drives SST changes as stable stratification suppresses ocean to air feedback. So the sign of the coupling and whether the ocean or atmosphere leads is fundamentally controlled by stability of the near surface atmosphere. And finally, to connect stability directly to surface temperature structure, I compare the skin temperature with Bock temperature. So here, the x-axis represents stability either from Bock SST air temperature difference in the upper panels or from the Munin-Obikov stability parameter in the lower ones. The y-axis shows whether the skin is cooler or warmer than the subsurface. That is whether we see a cool skin or warm skin regime. We find that most cases fall under unstable conditions with a cool skin, consistent with upward heat flux and active convection. Occasionally, during stable periods, we observe a warm skin. So that is when surface heating dominates and turbulence is suppressed. So again, the surface stability not only controls the direction of the air-sea coupling, but also the thermal structure of the top millimeters of the ocean, and in turn feeds back into the fluxes. Now that we've seen how stability affects skin temperature, let's look at what that means for flux calculations. Here, the bars compare the turbulent heat flux estimates under different stability regimes. The red bars show fluxes with a cool skin correction applied. The blue bars are without any correction, and the yellow bars use the measured skin temperature from the Seldon sensors. And the table on the right summarizes the temperature order among air, skin, and Bock SST in each regime. The idea for the stable conditions is that the cool skin correction was usually added in unstable regime. However, if it is added in stable conditions, that could even overestimate the flux magnitude doubly. So overall, when conditions are stable, the warm skin layer reduces the flux by about 9%, which can bias the Arctic heat flux if not corrected. So to wrap up, I'd like to leave you with 3 main points. First, the near surface stability of the atmosphere plays a dominant role in setting the direction and magnitude of air-sea heat fluxes, especially in the Arctic, where the boundary layer is often near neutral or stable. Second, the SST flux coupling coefficient can actually become negative under stable conditions. That means the atmosphere rather than the ocean can drive the variability, and the strength of this coupling can be as large as what we see over frontal regions in the subtropics. And third, the skin temperature in polar oceans isn't always cooler than the subsurface. During stable periods, it can be warmer, and that needs to be included in flux algorithms and satellite retrievals. So altogether, these results show that in the Arctic, it is not the mean wind or temperature that rules the air-sea exchange. It is stability that governs when and how the ocean can vent the heat into the atmosphere. And looking ahead, there are 3 directions I see for future work. First, we really need to develop direct eddy covariance platforms for the Arctic. Most of the existing data sets come from tropical and mid-latitude conditions. So extending these high-frequency flux measurements into the polar environment will greatly improve parameterizations like the core algorithm. And second, future studies should look at interaction between vertical and horizontal instabilities. For example, how mesoscale fronts or horizontal gradients can modify boundary layer stability and turbulent fluxes. I've looked at those in my other studies, but I have not yet implemented the mesoscale features, the horizontal mesoscale features into the Arctic regime. And third, we need ad hoc in situ measurements that combine both atmospheric and oceanic profiles to fully capture the coupled stability structure across the air-sea interface. So this is exactly where I'm taking this work next, moving from this bulk analysis toward direct flux observations and coupled stability diagnostics in the Arctic. So thank you for listening. I'd be happy to take your questions. If you'd like to check out more of our analysis, please check our paper here. And I want to highlight also our upcoming AGU 25 session on mesoscale air-sea interactions. And this session will focus on how mesoscale processes influence air-sea exchanges, including wind stress, heat fluxes, and coupled dynamics. So just a reminder that the early bird registration runs until November 6th. So that is the day after tomorrow. And we'd love to see your contributions and continue the discussion at AGU in New Orleans this December as well. So I'm able to take questions now. Thank you.
Thank you very much, Yanxu. So as usual, we can, if you have questions, you can raise your hand and then we can proceed with the discussion.
Yes, please.
If there are no questions, I can start with one. You showed us that in cold air advection or warm air advection cases, the stability is different, and this leads to a different spatial organization of the turbulence, right? You were showing with the spectra. So, yeah. Okay. So my question was, if you, I was curious to know if you had compared this with like satellite data, like low-level clouds, or if you looked at this into numerical models, or if you think it's not relevant for any reasons.
Yeah, I think it might be interesting to look at satellite data or model outputs, but I think there are some difficulties when we model the Arctic. First is because the Rossby radius is very small. So that means if we want to have some high resolution observations or some high resolution estimates from the satellites or models, we need really high resolution models to look at it, to compare with the in situ observations from the sail drones. So it's kind of difficult right now. And then also people are, and I would say the Arctic community, they care more about the ocean and about the interaction between the ocean and the sea ice, instead of what we are doing here, as to really look at the air-sea heat flux in the summer, and then to try to quantify how much of the extra heat or how much of the stable atmosphere can actually cap or just reduce the heat release into the atmosphere and store those heat into the ocean instead. So, but I still think this is a good comparison that we can consider in the future to compare the high resolution model with the sail drone data to look at the air-sea interface if the model can really contribute to what we can understand about air-sea interaction in the Arctic. Yeah, thank you, Ako.
Thank you. Please, Sarah.
Yeah, really nice talk. I'm curious, just on the most basic level, you're comparing 2020 and 2022 as a unstable versus stable years. What's the timescale for switching between unstable and stable conditions? Is it really the full year that maintains the?
No, it's only so because I only compare the data sets where we have the data. So if we look at the sail drone data over here of the time series is only from June until October, November, something. So it's only the summer period of time, and I think probably the precision can be low because the 2020 and 2022 they have different lengths of the time series, and then in statistics that means if we see 2022, oh okay, it's an unstable year, maybe it's just in this period of time we have more of those unstable events, but in 2022 if it's stable and then it's just because the time period is longer or there's some interannual variability, and then that leads to this variation between 2020 and 2022.
Thank you.
Hi, I have a question. I don't know how to raise my hand. Can you hear me?
Yeah. Hi, Megan.
Hi. Can you use under the stabilizing conditions, can you use that Mononovikov length scale as a height scale in any clever ways for, say, budget analyses? What's the meaning of that height?
I think the meaning of that height is, okay, I have my notes here. So the height, when it is smaller than 0, it means it's unstable, and with larger than 0 is stable conditions. And if it's very large and in absolute value, it means it's neutral conditions. So in neutral conditions, usually, so the wind is the dominant factor that can affect the air-sea heat flux instead of the stability as we define from temperature. So usually the most theory, we use that theory for, like, if we have the measurement from the direct eddy covariance, and then we rely on this most theory, we derive the what's it called, the flux profile relationships. Then we apply this flux profile relationship to our bulk algorithms, like the core algorithms, and then we can use such flux profile relationships into other regions where we don't have the direct eddy covariance method, but instead we can use this flux profile relationship and to estimate like remote or non-local regions. Because what I have to raise the question here is that usually for our air-sea interaction community, we do the eddy covariance in the tropical or subtropical regions, but instead in the Arctic, it's kind of very different from what we observe in the subtropical regions. So if we use the flux profile relationship that we derive in the tropical regions and then apply those to the Arctic, it does not make sense. So this is the basic idea of what I'm doing here.
Yeah, I guess I was just wondering if you can use that height scale in other ways besides just as a indicator of, you know, a kind of binary or tertiary indicator of yes, no, stable, unstable, neutral. I mean, could you use the value of that height for looking at tendency rates or processes, the kind of contributions to the air temperature tendency rates?
Yeah, I think I need to think about it more. But I think it's kind of internal, like the most theory is kind of internal for the Bach algorithm that we use, because we already think like the Bach algorithm, like the core, we kind of estimate the air-sea heat flux from the most theory already. So it's already there internally inside the algorithm we use. But I need to think about it more, like how this most, like the height and also the stability parameter can actually tell us how to modify our heat fluxes if we want to correct them.
Thanks.
Please, Shikar, go ahead with your question. Shikar, do you have a question to ask? I don't hear anything, so maybe we can move to Sarah. Shikar, we don't hear you, so if you can try to fix your issue and then try it again. So please, Sarah.
Hi, this was a super interesting talk. Thank you. I was curious, since your deployments are like covering different spatial areas in different years, I was curious if there was any spatial component to your analysis. Like, are some of these instability or stable regimes associated with being in a certain area, some of the marginal seas?
Yeah, I think some people are using the Sildron data to look at the wave field. Like, so the wave field will be more useful for the air-sea momentum flux instead of the air-sea heat flux. So I will say in this study, we focus more on the heat flux and then following kind of the time series instead of following the location of where the Sildron was actually located at. But we did this analysis, so of the sea surface temperature and the flux coupling coefficient calculation, and then the slope over here is actually the slope of the power spectrum with regard to wave number. But we did this, it's basically a kind of transition from the frequency into the wave number spectra, but actually I would still think about it as a frequency spectra, because we do not have kind of a spatial distribution of our measurements. We only have one line or several lines of the Sildron tracks. So it's more like time series instead of spatial field. But I know in the Sildron communities, a lot of people are looking at the wave field and the momentum budget. So if that can help, and people might know more than me. Yeah, thank you for your question.
Thank you.
Okay, so Shikar has written his question. So it's a clarification, and I read it out. I was expecting unstable conditions to have flatter spectra. Why is it steeper?
Expect. So this one, I would say, so my reasoning is that in unstable conditions, because the atmosphere can always bring the cold air into the region. So it's more like a large scale. And then if we think about the cold air coming from the North Pole into the Beaufort Sea or the Chukchi Sea is more like very persistent period of time. And then during that period of time, we have a lot of heat released from the ocean into the atmosphere. So I would conclude the unstable conditions to have more large scale and also slow motion scales. So compare with our stable conditions where the warm air advection is more intermittent. So that means the slope of our frequency spectra here is that the slope for the stable conditions, we have more intermittent or periodic events, like the warm air advection coming from the tropical region into the region. And so this means like the slope can be a little bit shallower compared with the unstable conditions, where it's more focused into the large scale and also the slow motion scales. So this is my kind of summary or my reasoning.
Yeah, so there is a next comment. Would not the shorter time scales have higher variabilities in unstable conditions? So it's probably referring to like convective motion. So the intermittency goes well with convective plumes in unstable conditions, maybe. To see.
Yeah.
Okay. Thank you.
Thank you, Ako. Yeah.
Are there any more questions? Sarah, you have another one, or is still?
Yeah, I think it's a clarifying question. For your analysis on turbulent heat flux, is this the result of using the core algorithm? Sorry if I missed that. Okay.
Oh yes, I missed that. I mean, I forgot to put that into like kind of a method slide. Yes, we use the core algorithm to do the calculation of air-sea heat flux. I know there are, so the seal drones, usually some people will just do the direct eddy covariance. I know some people do that, but for the Arctic missions, they don't have such W prime, T prime at the level of 5 meters, so I cannot do that. Instead, we rely on the core algorithm, but we turn on the cool skin effect and turn off the cool skin effect, or just try to use this real skin temperature. And in our last session to try to compare whether we should use the cool skin corrector if we have really a warm skin. So yeah, this is what we did. Yeah, thank you for asking this question. Yeah,
I was just like curious if like some of the you went over the history of the core algorithm and said that it's more effective for tropical and subtropical regions, and so I was just curious if there's any like inherent biases that you think are in the estimate that could influence your results because you're using core to calculate fluxes.
Yes. So definitely yes. But that one, if it's internal, like inside the core algorithm that we cannot control, but at the end, what we would like to say here is that, for example, during our unstable conditions, and then so usually we have a cool skin. Okay, I do not have my, okay, yeah, I have my cursor. So so usually we have a cool skin. And if we use this cool skin, that means our turbulent heat flux is smaller compared with using the box sea surface temperature from kind of below the sea surface. But then if we have a stable condition, we have the air is warmer than the ocean. So if we still apply the cool skin temperature, this will increase the sea air temperature difference. And then that can actually be biased. So instead, we should really use the like kind of apply a warm skin effect or something into the core algorithm, because instead during the stable conditions, what we have usually is the ocean surface, the skin temperature is warmer than the subsurface. So if we instead use the cool skin correction of what we had in the tropics or subtropics, and that can really affect very much for the heat flux. But here, after our calculation, it's just about 10%. Maybe it's because usually in stable conditions, the stable conditions, usually we do not have such a large difference between the sea air temperatures. So in total, like the effect is small for our statistics, but I think this is something we need to consider if in the future we want to implement that into coupled models or something like that.
I see. Thank you so much.
Thank you. So please, Sarah.
Yeah, I just maybe to ask a final question or a near final question. You finished up by making a case for measuring across the air-sea transition zone. And so that's an interesting recommendation. And I wondered if you had specific views on what the observing system requirements might be or how that should be done based on your research.
Yeah. Can you be more specific? Because I don't quite understand.
Well, I think you made a case for measuring the upper ocean and the atmosphere together.
Oh, okay. Yes, at the end.
Yeah.
Yeah. So basically, I think it might be interesting if we can develop kind of in situ instrument that can put the atmospheric stability and the ocean stability together as one entire system that we can put in at the air's interface to have an idea of both the ocean surface layer and atmospheric surface layer. Because I know, so even though I studied atmospheric stability, I know a lot of the ocean community, they care about the ocean surface layer and how they are affected by heat fluxes. So they treat the atmosphere as a forcing for the ocean people. And then they would like to know how the heat flux, like seasonal heat flux variations might affect the structure, the stability of the surface ocean. So I think it might be interesting if we have kind of combined platform at the air's interface that we can both measure the atmospheric stability and the ocean stability, and then try to look at the time series of how the entire system might evolve in time, rather than to say, okay, the ocean is the driver or the atmosphere is the driver.
That sounds like a great idea. Do you think it could be done from a sail drone type platform, or would it take something really different than what we have now?
Yeah, I think it might be great for the sail drones to have it. But I think also people are using wave gliders to do this type of work, and that they are trying to develop this kind of platform as what I've concerned about. So I think, yeah, I think this is a great idea to do this. And then also, I think the ocean community, they really would like to have the vertical profiles of either temperature or salinity or something. But for the air-sea interaction community, we care more about only at one certain level, how much the heat flux is. So we do not, at the moment right now, we do not really have this kind of platform that we can develop a profiling kind of data set where we can have an idea of the near surface stability instead of at a certain point, but rather it's kind of profile. Yeah.
Yeah. Cool.
All right, very nice. And if there are no more questions, I think we can close it here. Next week is vacation, so we skip the seminar. Is it correct, Sarah?
Yeah, it's a holiday in the US, France, other places maybe.
Yeah, so we reconvene in 2 weeks from today. All right, thanks a lot for joining, and thank you again, Yanxu, for your presentation.
Thank you, Ago.
Bye-bye, everyone. Bye, thank you.